Okay, class. So in the last class, we were completing this thermal properties of matter. So let us just end this topic. This is conduction, convection, and radiation were the points that we discussed in the last class. Now we have to complete the Stephen's law and the Wien's displacement law. So who is there? Abir, Ali, Jobita, Jesleen, Zainab. Okay. So coming to the Wien's displacement law and the Stephen's law. So see, when we are discussing about these laws, these are completely related to your thermal properties of matter, right? After this, we'll be starting with the thermodynamics. So when we're talking about this Wien's displacement law, this is basically giving you a relationship between the wavelength and the temperature. It just says that the wavelength is inversely proportional to the temperature. So you write this law as lambda m is equal to B by T. What is lambda m? Lambda m is the wavelength at which maximum energy is emitted. Okay, it's the wavelength at which maximum energy is emitted. And B is the Wien's constant. This is the Wien's constant whose value is 0.002829 millikelvin. This is the constant's value. And this is the wavelength at which maximum energy is emitted. And what is T? T is the temperature. So see, what is important here to remember is that wavelength is inversely proportional to temperature. This is important, and most of the questions will be from the ratio part. You'll have to calculate the ratio of the quantities, so this will be used. The ratio calculation part will be used. Okay, coming to the Stephen's law. So what is the Stephen's law? Stephen's law tells us about the relationship between the energy that is emitted and the temperature. Wien's displacement law told us about the wavelength. Stephen's law tells us about the energy and the uh, temperature that is present. So the law basically says that E stands for the energy. E is equal to sigma T to the power 4. See, energy is directly proportional to the temperature's fourth power. Okay. And the constant that you use here, this is called the Stephens-Boltzmann's constant. Okay. Stephens-Boltzmann constant. So Boltzmann you must have heard already. So Stephens-Boltzmann's constant. So this is Stephens-Boltzmann constant. What is E? E is the energy radiated by the body. One more thing, here you have emissivity also. Emissivity we have studied, but emissivity is equal to 1 for perfectly black bodies. Okay, this is equal to 1 for perfectly black bodies. That's why the formula that we use for E is mostly written as sigma T to the power 4. Or it is also used as E T to the power 4, like this also, E T to the power 4. Now, value of this is what? This is the energy. Okay, I've written it here. Coming to this value, this is 5.68 into 10 to the power minus 8, the value of this Boltzmann constant. So let me write it down here. 5.68 into 10 to the power minus 8. This is the value of the Boltzmann constant that is present. 5.67 into 10 to the power minus 8 joules per second per meter square per Kelvin. Not even per Kelvin. This becomes Kelvin to the power 4 in the unit. So let's see some questions. Okay. So this says a spherical. Okay, do one thing. Write it first. Perfectly black body's definition was left in the last test. What is a perfectly black body? This is one which absorbs all the radiation. So the process of absorption is high and complete in this. Please write down these two laws. Then I'll start with thermodynamics.
Can you scroll up?
Okay, class. So this question says that a spherical body with radius 12 centimeters radiates 450-watt power at 500 Kelvin. Then it says if radius were halved and temperature doubled, radius is halved and temperature is doubled, what would be the power radiated? See, you will use the Stephen's formula here. So E is equal to A sigma T to the power 4. We are calculating the power radiated. So we'll multiply area also, okay, for the total power. Now see, if the radius is half, what is the how much power has been generated? 450 watts. See, original power that you have is 450 watt. Now, when you are squaring, when the radius has been halved, okay, so this will be energy. This will be 4 spherical body is there, so 4 pi r square. Now radius r by 2 whole square is there, t to the power 4. Okay, rest of the, okay, temperature is also doubled, so this becomes 2t to the power 4. Right. Now if you look here, E is equal to A sigma T to the power 4. You have 4 pi r square, 2T to the power 4. This is to the whole power 4. See, two twos will be cut and these two. So 4 will be left. If you take the ratio of E1 and E2, this will be, I'm writing this as 4 pi r square. This will be 4 pi r square. So when you take the ratio of E1 by E2, this will become 4 pi r square sigma T to the power 4. This will become 4 pi r square. 4 will go up. Here you will have 4 into 4 because it is T to the power 4. T to the power 4. So 4 will be cancelled. It will be 4 times the original power. So 4p, yani 4 into 450. So this is 0, 0, 16, 17, 18. 18 watt. Okay. Write this question. Done.
No, ma'am. Yes.
Okay, this question says how much faster does a cup of coffee cool off by 1 degree from 100 degrees Celsius? So this is the change in the time period. Then from 30 degree Celsius in a room at 20 degrees Celsius. Now, in the first case, you have the temperatures 1 degree and 100 degree, right? And in the second case, you have the temperature 30 degree and 20 degrees Celsius. So, when you are, how much faster it is saying, does a cup of coffee cool off by 1 degree from 100 degree? It has started. So, you have to apply the Stephen's formula. E is equal to sigma T to the power 4 minus T naught to the power 4. Basically, change in temperature's fourth power. This is what you have to consider. Now, you will just take two equations. See, sigma will be cancelled. Basically, you just have to see the energy differences between the temperature differences between the all of these. Okay, so here if we see the temperature, we have to convert it. C class, because differences and then the ratio is given. So here it's better on the safer side if you convert, because the answers will be different. Because we are not just simply taking the difference and keeping it. We are taking the ratio also. So even will be, so in this will, when you'll convert it, so 373 to the power 4, 293, 293 Kelvin. 293 Kelvin to the power 4. To the power 4 divided by the next one is 30 and 20. So 303 Kelvin to the power 4 minus 2. Again, it will be 293 only. So 293 to the power 4. This you have to solve and just check. Answer should be around 11.32. Done, class?
No, ma'am.
No, ma'am.
One 1.09. I think check the calculations once again, whether it's 10.9 or something. Okay, anyways, you can calculate it later. Tell me whatever answer is there in the next class. Now I'll be starting with thermodynamics. So firstly, we'll start with the laws of thermodynamics. So you have various laws, first law, second law, zeroth law is also there. Now coming to the thermodynamics, what is thermodynamics? See, we have completed the thermal unit. We had the properties of bulk matter. In the properties of bulk matter, you have two groups. One is regarding the mechanical properties, other is regarding the thermal properties. So in mechanical properties, we have talked about the mechanical properties of solids and we have talked about the mechanical properties of fluids that we have done. Now we have the thermal properties of matter that also we have completed, both liquids and solids. There we have completed. Thermodynamics is the different branch. It will now be dealing with work done. The entire concept of work done was hidden. We didn't use the concept of work done till now. So the concept of work done will be utilized here. So yes, let's start. The branch of physics which deals with the relationship between heat and work. See, heat and work is called thermodynamics. See, dynamics means only which is related to work done. Your static part is left. Statics opposite is dynamics. Now, you have to understand first the meanings of systems, surroundings, and all. So what is system? System is that part which is under your observation. You are considering it that time. For example, we discussed this, I think, in work, energy, and power also, in laws of motion also, in rotation also. I've told you several times this concept of system and surrounding. Now here in your thermodynamics, it has proper formula over here, and here it has proper definitions to be used. So you'll have to keep the definitions also in your mind. Okay. Now starting with this, the system, the example I think I gave you was a glass of water, right? So example, glass of water. So the part, that glass of water, just the glass of water that is present, that is under the thermodynamical consideration. So only the glass of water is the system. Apart from the glass of water, anything that is existing, even I am existing apart from that glass of water. So for me, any force that I'll be applying will be the external part. Means I'll not be the part of system. If I'm considering myself and the glass and the table as the system, so only three of us will be considered as the system. So system means the part of the thermodynamical consideration which you are considering for that time. Okay. Now systems are of three types: open, closed, insulated. Open means there is exchange of matter and heat with the surrounding. Enclosed, there is exchange of only heat, and insulated, nothing. Neither heat nor the matter can be exchanged. So these are the three types of systems that are present. Coming to the surrounding, everything outside the system can have a direct impact on system is surrounding. Like I said, the glass is there. This glass is there, which I have filled it with water. Okay, this is the glass. Now, only this is the system. This is only the system. Rest of the things which are present, they will be a part of the surrounding. So I can say my system plus the surrounding make up the universe. Okay, the whole universe. I'll write it till here, then I'll discuss further things. A written class?
No,
No,
ma'am.
ma'am. 1 minute.
Of your chemistry, you must have done. Yes, class. I was saying that in chemistry, class 11th, you have thermodynamics. Yes or no?
Ma'am, you're
Am I
lagging.
audible to all? Class, is the voice better?
Yes, ma'am.
Okay, I was saying that you must have done states of matter. There, these are included. Also, I was asking, do you have thermodynamics in chemistry class 11?
Excuse
Okay,
me.
then it would be there in 12th. Anyways, when I'm talking about the thermodynamic parameters, I'm still lagging. Class, is it fine now? Please now confirm.
Yes, ma'am.
Okay, states of matter is cancelled. Okay, and thermodynamics?
We have it in chemistry, ma'am.
Okay. Okay, states of matter is now cancelled. Okay. See, physical quantities that define the system. So we'll be talking about three quantities in detail. One is the pressure, another one will be the volume, and the third one will be the temperature. Now, equation of state, relationship between the thermodynamical parameters. So you have an equation, PV is equal to nRT. This is the equation, PV is equal to nRT. P is what? P is the pressure, V, I'll write it. P is the pressure, V is the volume, N is the number of moles, R is the universal gas constant, and T is the temperature. So this is the relationship between between all of these when we're talking about the equation PV is equal to nRT. So this is in case of ideal situation. So we'll be talking about it. But before this thermal equilibrium, we have discussed it in the thermal physics also. Let's say the temperature of first body is A, second body is B. Let's say T2 is greater than T1. So some amount of heat will flow till the time TA becomes equal to TB. So two bodies are in thermal equilibrium if they have the same temperature. And what all thermodynamical equilibrium? See, this is thermal equilibrium. Just when the heat is flowing to make the temperature same. You have the thermodynamical equilibrium also. Like thermal equilibrium means you have the temperature same. Then you have mechanical equilibrium, you have chemical equilibrium. Now you have to focus on the thermal equilibrium. Okay. System is thermodynamical, means your pressure is constant, volume is constant, temperature is constant. Then you say your system is thermodynamically in equilibrium. Now, what is the zeroth law of thermodynamics? See, suppose, look at this example. This is very, very easy law. This says that suppose this is a room. This is a wall, yellow one, and this blue part, this is also a wall. So A, B, C, these are the three areas available, A, B, and C. Now look here. This wall, this orange wall, this is isothermal wall. Isothermal wall means it has a constant temperature, but it is a conducting wall. We'll be talking about all these processes, isothermal, adiabatic, so you will see the conditions. Right now for isothermal, just understand that the temperature remains constant. So it's a conducting wall. Conducting wall का क्या मतलब हो रहा है? Conduction possible हो पा रहा है. Means the heat is able to be transferred across the wall. That is your isothermally conducting wall. When we are talking about this blue one, this is an adiabatic wall. You have the adiabatic and isothermal component. Means non-conducting. This won't allow the heat to be exchanged. This allows the heat to be exchanged. Isothermal wall means conducting wall. This allows the heat to go. Adiabatic doesn't allow. So suppose I say this is a conducting wall. Okay. So from A to B, the bodies will be having exchanging heat, and till the time they'll exchange the heat. At which time? Till the time they achieve the same temperature. So temperature of A will eventually be equal to temperature of C, because this wall is conducting. There will be a conduction between these two. So this will allow the conduction to occur. Now, between A and B also conduction is possible, because the wall is conducting also here. It is still conducting. So temperature of A will eventually be equal to temperature of B. But see, the temperature exchange between B and C was not possible because the wall was non-conducting. So what is happening here if the wall is non-conducting? No temperature exchange. But according to this, look, TA is equal to TC. TA is equal to TB. So we can say TB is equal to TC also. Temperature in B is equal to temperature in C. Now let's read the statement of zeroth law. This says these are the laws of thermodynamics. Two bodies or systems that are in thermal equilibrium with a third body are in thermal equilibrium with each other. They were in equilibrium with the third one, A, so they'll be in equilibrium with each other. That is what is meant by it. And last point before we go on to the statement of work done, internal energy. So internal energy, when I'm talking, I think I mentioned this earlier also, that I'm talking about kinetic energy and I'm talking about the potential energy. One is your kinetic energy, other is the potential energy. So your internal energy is made up of the kinetic energy plus the potential energy. But in ideal situation, we use potential energy as 0. So maximum time the internal energy becomes equal to the kinetic energy. So these are some basic points you should know for thermodynamics beginning. I'll start with work done, but write down these points first. Is it clear till here to everyone? Abir, Ali, Jobita, Jesleen, Zainab, understood?
Yes, ma'am. Can you scroll up?
Done. Okay, class. Coming to the work done. So this is related to change in volume. Means there is an initial volume and a final volume. Let's say V1, this is the initial volume, and this V2, this is the final volume. So work done is P delta V. Remember this formula for work done. P is the pressure, delta V is the change in volume. Okay, pressure change in volume. Provided your pressure is constant. One thing also is there for the utilization of this formula, that pressure has to be constant. Let's say the pressure is variable. Okay, so we will use integration because it's variable. So P dV we are going to use from V1 to V2. And when I say P delta V means properly calculate the change in volume. That is this V2 minus this V1. In integration, we have the limits to put, so it's okay. Let's see the question. This, see here, in this question, the pressure is given as 10 to the 10 pascals, and change in volume is given. See, what will be the change in volume? Initial volume is 5, final volume is 25. What will be the change? Yes, Abhi, right. 20. Yes, Ali, correct. 25 minus 5, this will be 20 meter cube. And pressure is also given as 10 pascals. So work done, see, pressure is constant. There is no X, Y, Z, nothing. So this will simply be 10 into 20, which is equal to 200 joules. Now see, look at this question. Okay, this question I'll tell you. First, you will try this question by yourself. Write down this. Okay, Zainab, take 5 minutes break, everyone. Then after 5 minutes, I'll continue this. All right. So just don't leave the meeting. Stay connected here only. Okay, I think enough time is there. Let us continue now. 5 to 10 minutes have gone. Uh, yes, Jobita, at 11. 11 means IST means after half an hour.
Okay.
Okay, so see, this says that now see here in this question, the pressure is variable. If you see, look here, the pressure is variable 3V. So V, this is not given 3 pascals. This is given, pressure is given as 3V, means pressure is dependent upon this V. So how we'll calculate work done? It will be P dV integral from V1 to V2. So see, this will be 3V dV integral from 1 to 3. Now, this is equal to 3 V square by 2 when you will integrate, and limits are from 1 to 3. Now, let us put the limits. 3 by 2 into 3 square minus 1 square. So, what we'll have? 3 by 2 into 9 minus 1. So, this will be 3 by 2 into 8, 3 into 4, which is equal to 12 joules. I hope everybody remembers the integration. V to the power n is written as V to the power n plus 1 divided by n plus 1. And then you put in the limits V1 to V2 instead of V1. Upper limit minus lower limit. Quickly write this, class. Now, see, the work done is given by the area under the graph, because work done is pressure multiplied to the volume. No? So whenever you have multiplication, the third quantity is always given by the area. Now see, if there is expansion, work done will be positive. If there is compression, work done will be negative. Like this, if you get the graph, pressure versus volume. See, this is inversely proportional. So you're getting a hyperbolic graph. Now this area that is enclosed, this area will give you the work done. And suppose for a cyclic process, we are seeing a clockwise direction, then work done will be positive. Otherwise, work done will be negative for anti-clockwise. Like, look at this. This is a triangle. This actually looks like a triangle. No? So simply, if I have to calculate the work done, the area will be simply the area of the triangle. What is the area of the triangle? Half into base into height. So half, base is 10, height is 5. So this becomes 25 joules, like this. And see, if it's a cyclic process, now see, you have to check expansion and compression also here. So that will be given by the arrow. See, here the volume is increasing, means there is expansion. This is, so expansion is positive. We are writing it as positive. What is cyclic process? It's the process when the initial point is returned. So let's say A point is there, B point is there, and C point is there. So A to B, B to C, and C to A, like this. So this is what is a cyclic process. In the graphical portion also, you will notice a graph is like this. And here the pressure versus volume graph is given, and something like this is given, A point and B point. And this is pressure versus volume, like this. So suppose you're calculating this. This will be area here. See, this will be the area of the graph also. This will be the area of the graph. So this is a rectangle, 10 and 20. So you will calculate the area of the rectangle. That will be simply length into breadth. So length into breadth, 10 into 20. This will become 200 joules. Now look, what is the direction? This is going anti-clockwise. And anti-clockwise, you've seen it's negative. So this work done will be minus 200 joules. Okay, like this is how you have to write. Please copy down this PV diagram part.